Hello everyone, I'm an avatar developed by Yili Lin, a PhD student in health services research at George Mason University. Today's session will cover how to interpret the results of logistic regression in R. The key components of logistic regression output include coefficients, estimate, standard error, z-value, p-value, and model fit metrics, null deviance, residual deviance, AIC. A generalized linear model, GLM, was fitted using a binomial family, indicating a logistic regression. The dependent variable, Hass-Cancer, is binary. The model allowed for a maximum of 100 iterations in the Fisher scoring algorithm to estimate parameters. The coefficient estimate represents the change in the log odds of the outcome for a 1-unit increase in the predictor variable. A positive estimate increases the odds of the event, while a negative estimate decreases them. In this example, the intercept coefficient is negative 10.88, indicating the log odds of having cancer when all predictor variables are 0. A 1-unit increase in integument increases the log odds by 2.28. The odds ratio, OR, provides an intuitive interpretation of coefficients in logistic regression by expressing the relationship between each predictor and the outcome in terms of odds. To calculate the OR, exponentiate the coefficient estimate. For example, a unit increase in integument increases the odds of having cancer by approximately 881%, indicating a very strong effect. The standard error of the coefficients measures the uncertainty of the coefficient estimate. A smaller standard error indicates greater precision, while a larger one suggests more variability. To assess the reliability of the coefficient, compare the standard error to the coefficient itself. If the standard error is large relative to the coefficient, the estimate is less reliable. For mediastinum, a standard error of 0.06 indicates some variability, but it is not excessive. The z-value indicates how many standard errors the estimate is from 0. A larger absolute z-value provides stronger evidence against the null hypothesis, which states that the coefficient is 0. Here, a z-value of negative 2.55 suggests that the estimate is approximately 2.55 standard errors away from 0, indicating that the effect of mediastinum is unlikely due to random chance. The p-value represents the probability of observing a z-value as extreme as this, in absolute terms, if the null hypothesis is true. A small p-value, typically less than 0.05, suggests statistical significance, allowing us to reject the null hypothesis and conclude that the variable meaningfully affects the outcome. In this case, the p-value of 0.0107 indicates a 1.07% chance of observing a z-value as extreme as negative 2.55 if mediastinum had no effect on the outcome. Since this p-value is less than 0.05, we consider mediastinum to be a statistically significant predictor of cancer risk. Significance codes visually represent the p-value of each coefficient, with 3 stars indicating strong evidence of a significant relationship between the predictor and the dependent variable. The null deviance measures the fit of a model with only the intercept, predicting the outcome using the overall mean of the dependent variable. A higher null deviance indicates that this simplest model explains the data poorly. It serves as a baseline for comparison with a full model that includes predictors. The degrees of freedom associated with the null deviance is the number of observations minus 1 for the intercept. The residual deviance represents the deviance of the fitted model with all predictors, indicating how well these predictors explain the variance in the outcome variable. A lower residual deviance compared to the null deviance suggests that the predictors significantly improve the model's fit. The degrees of freedom for the residual deviance is calculated as the number of observations minus the number of estimated parameters, including the intercept. The difference between the null deviance and the residual deviance reflects the improvement in the model's fit by including predictors, indicating that the model explains a significant portion of the outcome's variance. Logistic regression lacks a direct equivalent to the R-squared statistic from linear regression, but McFadden's R-squared is a commonly used measure of model fit, ranging from 0 to 1. It's important to compare pseudo-R-squared values only within the same dataset. In this model, McFadden's R-squared is approximately 21.8%, indicating that about 21.8% of the variation in cancer occurrence is explained by the model. A McFadden's R-squared between 0.2 and 0.4 suggests a good model fit for logistic regression. The Akaike Information Criterion, AIC, is a measure of the model's goodness of fit, adjusted for the number of predictors. Lower AIC values indicate a better fitting model. The logistic regression model assumes that the variance in the binary response variable is accurately modeled by the logistic function, following standard practice for binomial models in generalized linear models without requiring adjustments for dispersion. The optimization algorithm for estimating the model parameters converged after 9 iterations, indicating an efficient and stable fitting process for the logistic regression model. Understanding these components aids in evaluating models and applying logistic regression to real-world data.